Hey, I hope you realize that last week's discussion of stellar evolution barely scratched the surface. There are a lot of things that could, and I hope you will, follow up on. But we were left with an interesting question at the end. If you have a stellar core whose mass is below the Chandrasekhar limit of about 1.4 solar masses, it forms a white dwarf. If it's more massive, electron degeneracy will not hold the core, and the core collapses further, forming a neutron star with a density much, much larger than a white dwarf. But neutron degeneracy will maintain the mass of a neutron star up to maybe 2 or possibly 3, depending on what you think of the nuclear equation of state solar masses. What happens if the stellar core is more massive than the neutron star limit? What happens then? As many times in this class, the answer to this is going to require us to step back and start over, learning some new fundamental physics. The physics we're going to learn in order to understand this is going to be, of course, the theory of relativity. And we're going to step all the way back to enunciate the principle of relativity and see where it takes us. So, what is this principle of relativity? It's a thing that was known in ancient times. It was articulated first very clearly by Galileo, to my knowledge, but not very concisely. What Galileo is saying in this lengthy quote from his dialogue from 1632 is that if you are in an enclosed room on a ship, in a cabin, and you do whatever physics experiment you want, you will not be able to distinguish the situation where the ship is at rest at anchor or the ship is slowly moving through calm seas. The laws of physics do not allow you to make an experiment that tells you whether you are at rest or moving at a constant velocity. Now, Galileo didn't know the math that underlies this, as we know. The math was articulated by Newton, but we understand it. Newton's law, F equals ma, this is everything, remember, says that the laws of physics determine the accelerations of objects. Turns out is that when you measure the acceleration of something from a laboratory that is at rest, or you measure the acceleration of the same object making the same motion from a lab that is moving with a constant velocity, you get exactly the same answer. There's a bit of calculus hiding under there. Let's do a graphic demonstration to make this clearer. So, what we have here is essentially the simulation we used to describe uniform circular motion. We have here a red dot that is moving uniformly around in a circle around that point in the center. We have a red arrow pointing to the dot, which tells us its location relative to the center. The blue arrow, remember, is its velocity vector. Its speed is constant, but its velocity is changing. And the green arrow, therefore, signifies the acceleration that you measure when you see something moving in a circle. And the acceleration points at the circle. If this were a planet orbiting a star, we would ascribe this acceleration to Newtonian gravity, an attractive force between the star and the planet. Now, this is all drawn in the situation where the star is at rest. Question now is, what happens if we observe this same physical phenomenon, but we are sliding to our left, or to the left in this image, at a constant speed, or constant velocity, since the direction is constant? Well, in that case, what we would observe is essentially the same motion, but shifting slowly to the right, and here is what it would look like. This is the same object, but superimposed on that is a slow drift to the right, which is what you would observe if you were drifting slowly to the left. And you see that the motion is a little bit more complicated. In this image, we've added on, as we did then, the velocity vector, and you see that unlike the previous case, the magnitude of the velocity, the speed is not constant, the object is moving faster at this point and slower at this point. The motion is more complicated, but it becomes clearer if you do what we did last time and pull off the velocity vector and draw in the bottom picture, the velocity vector is the blue vector, and you see that the blue vector indeed is moving around a circle, but the circle is simply shifted. The velocity with which this planet is now moving is given by some constant magnitude vector which rotates. That's the black arrow that is the auxiliary arrow in the image on the bottom, added on to a constant shift to the right, which takes account of the fact that we are drifting to the left. And indeed, if I then compute the rate of change of the velocity, the acceleration, Then in the bottom panel here, you can see the green arrow, which indicates the rate of change of that blue arrow, and you notice that the magnitude of that green arrow does not change, and in fact its direction is always tangential to the circle, and if you move it, what you see in the upper panel is that if we were observing the acceleration of this planet, we would observe an acceleration that is always directed towards the center of the circle as the circle drifts to the right, and we would say, aha, there is a gravitational force between something at the center of that circle and the planet. We would derive the same physical laws from this drifting system that we would have had the star been at rest. So that helped you visualize the fact that because Newton's law determines an acceleration, you would observe the same laws of physics when you added a constant drift velocity to whatever it is that you were observing. So we're going to elevate this observation, if you wish, into a principle. And the principle says that since there are no measurements you can make that will detect whether you are at rest or moving with a constant velocity, in fact, since you can't measure it, the question of are you at rest or moving with a constant velocity, or what is your constant velocity, is in fact not a proper physical question. There is no such thing as being at rest. It makes no sense. There is no cosmic rest frame, though maybe there is. We'll come back to that in the last week of the class. But at the level of the laws of physics, moving at a constant velocity is all you can say. You can claim that you are not accelerating. If you were accelerating, you would note the effects of acceleration. We saw that the effects of acceleration are measurable. When someone hits the brakes in your car and you go flying at the windshield, you know the car is accelerating. But a constant velocity of motion is unmeasurable, and therefore the only thing you can ask is, what is your velocity relative to some other system? And absolute rest does not make sense. This is the principle of relativity, and it's going to be the central philosophical point we follow this week, and of necessity this week veers a little bit into philosophy. What we're going to do is we're going to take this principle, adopt it as a property of the universe, and ride it hard. We're going to see what it tells us. And as we'll see, Newtonian physics is very nicely consistent with this. We'll do some explicit studies to see that. But Maxwellian electromagnetism is not consistent with the principle of relativity unless you make modifications to what you mean by space and time. And after some hesitation, we will adopt Einstein's solution, which is Maxwellian electrodynamics is correct. Our ideas of space and time need modification. That modification is Einstein's special theory of relativity, and I hope that we'll be able to really understand what that theory means and what its implications are and how this is derived, both philosophically and at the level of being able to compute things and solve some problems. Once we have this, we can follow in Einstein's footsteps and say, okay, now we understand a modified principle of relativity. All physics must now obey this modified principle of relativity. Electrodynamics is fine. It'll turn out the nuclear forces are fine. Good old Newtonian gravity is not. Newtonian gravity will be discovered to be inconsistent with our new principle of relativity. And modifying this is what led Einstein, after a decade of hard work, to the general theory of relativity, which is a modern view of gravity. Now, there are two things that I want to emphasize here. One is that the special theory of gravity is something that we will be able to actually understand at a technical level, and your average working physicist has a good understanding of the special theory of relativity. The general theory is mathematically and conceptually much more involved. We will hopefully be able to understand some of the conceptual issues. The technical aspects of GR are unfortunately something we will not be able to master. So we will be a little bit more impressionistic in our description of general relativity. But we will describe what the theory says and how it's constructed and some of its more astronomically interesting consequences. And finally, we'll apply it to the important question of what happens to a star whose core is too massive. I want to make one other philosophical point before we go on to actual work, which is this is going to be a great example this week of the way that science proceeds by a sequence of successively better approximations to the truth. What Einstein's theory of relativity is going to do is, in a philosophical sense, overthrow Newtonian ideas completely. We're going to have to say that Newton was philosophically fundamentally wrong, but on the other hand, we're going to have to also figure out that all of the calculations and the predictions and the measurements of stellar masses and so on that we very successfully performed and verified observationally using Newtonian physics are still valid. The way that this works is that if you take a suitable limit in the parameter space under suitable circumstances, Einstein's theory of relativity reproduces the results of Newtonian physics, and we're going to have to keep that constantly in mind because Newton's physics is not wrong. It may be philosophically misguided, but at a technical level it produces correct predictions when applied under the right circumstances, and indeed Einstein's theory will reproduce the results of the old theory in the suitable limits, and this is definitely the way that new scientific theories do not completely overthrow the old, but actually understand them as being valid in a limiting case.